Graph Theory Class 11 Video 1. In this video we're going to look at some examples of colouring graphs. In particular we're going to look at colouring maps. So let's begin with the problem. The question is just, how many colours are needed to colour the following map so that no neighbouring states are the same colour? Okay, so it's a really simple question, and you could pose this question to like a 4-year-old or something and they might be able to solve it. Like, you just need to start colouring in the states like this. Like Washington and Oregon, they share a border, so they have to be a different colour. I don't know what this state is, but it shares a border, so it has to be a different colour. Montana doesn't share a border with Washington, so that can be green again. Okay, and you just continue in this way. I could do this one yellow for no particular reason, and on and on and on. And the question is, what's the fewest number of colours needed? Like, for example, maybe it was a dumb idea to do this one yellow, because I could have done this one red. Oh no, I can't do it red, but I could do it blue. I can do it blue. Right? That's still legal. And I could try and continue, and I could try and see what's the fewest number of colours I need. So, for example, this colouring right here, which I just found on Wikipedia, this uses how many colours? Well, I see 1, 2, 3, 4, and you probably can't see that, so I'll try a different colour. So like this one, like peach, purple, yellow and green. So it uses 4 colours. But the question is, can we do better? Like, can we colour it with just 3 colours? Okay. Well, it's a complex question, right? There's lots of states, and just trial and error could last a long time. So instead, let's try and think of a way of analysing this problem mathematically. Okay. So to do that, first, let's consider a simpler problem. So in this example, I want you to turn this map. This thing here is a map. Okay. It's like these are the countries, and the borders are the green lines. So this thing here is a map. Okay. So turn this map into a graph and find the minimum number of colours needed to colour it. So how do I do this? Well, I'm just going to put a vertex down for every country or state or whatever you want this to represent. Okay. And then I'm going to draw an edge if these states share a border. Like this, like this, like this. And I'm trying to keep it neat so it's clear. Okay, so it looks like this. And then I'm going to redraw it so that it's clearer to understand what's going on. So I think if we redraw this, we simply get something that looks like this. Okay. So the question of how many colours are needed to colour the original map, it's the exact same question as how many colours are needed to colour this graph, or what is the chromatic number of the graph. So the new question is, what is the chromatic number of this graph right here? And this question is, it's directly equivalent to the question of how many colours are needed to colour the map. Okay. Well, we spent a previous video talking about chromatic number. Okay. For this graph right here, maybe I'll try and find a minimal colouring. So if I try and start colouring in some vertices, I'll colour this one green, maybe this one pink, this one yellow, this one blue, I'll do this one green, this one pink, and this one yellow. So this is a 4 colouring, so that we know that the chromatic number is less than or equal to 4, okay? But also, if you look closely, you'll realize that this graph right here has a clique hiding inside it. It has a K4 hiding inside it. So that means, by some theorem, that the chromatic number is greater than or equal to 4. It's greater than or equal to the clique number, which is 4. Okay? So put these two bits of information together, and what do they imply? The chromatic number equals 4. So that means that, if I can write more clearly, it might be easier to read. That means that this graph right here requires 4 colors to properly color it. So that means that the original map, this original map, which is now hidden underneath all of my white lines, so this original map, which I'm going to reveal right now, this requires at least 4 colors to color it, with no neighboring states the same color. And you can apply this technique to trying to solve the same problem for the United States of America, right? Like, you could turn this map here into a graph, and then you could try and find the chromatic number of that graph. It's a bit difficult, right? But I mean, for a computer, this would be an easy task. For us, the graph would be a little bit big, okay? So now I want to talk about maybe one of the most famous theorems in all of graph theory, okay? And it's to do with coloring maps. Yeah? So the theorem is as follows. Okay. It just says that any map requires at most 4 colors to properly color it. And when I say properly color, I mean color it so that no neighboring states or no neighboring cities or counties or whatever your map represents have the same color. And this theorem is called the 4-color theorem. Okay? So it says that you need at most 4 colors. Sometimes you can do it with fewer colors. Like, I think if you actually try and work out how many colors the US needs, you can do it with just 3 colors, I think. But not every map is possible to do it with 3 colors. Like, if you look at trying to color in South America with just 3 colors, you're going to need, it's going to be impossible. And for example, our map right here, we tried to find the minimum number of colors needed, but it turns out you need 4. Okay. So this theorem here is probably one of the most famous theorems in graph theory, and it's also one of the most famous theorems in mathematics, really. It's a very, very old theorem. In fact, it was first conjectured in 1852. So that means, like, in 1852, someone was like, hey, I think this is probably true, but I can't prove it. Okay? And then it took a bunch of years until 1879 when someone announced a proof. Okay, so it took like, 27 years until someone announced a proof. And then everyone was happy for a while until 1890 when someone found an error in the proof. So someone actually went back and sort of reread this proof, and they realized that there's a mistake in it. Okay? And then everyone went back to the drawing board and they tried to solve this problem, and it took a long time. It took another 86 years until another proof was announced. Okay? And this proof people have generally come to accept as good enough. It's a correct proof. Okay. One more thing which is like noteworthy in this, relating to this subject, is this proof right here. It was sort of a bit controversial at the time because it heavily relied on computers. And nowadays this might not seem like a big deal because everything heavily relies on computers, but the idea that a mathematical proof somehow used computers in an essential way was a bit of a shock at the time. I mean, what basically happened is the people who proved this in 1976, they reduced the proof down to checking an insanely large number of graphs. Like, there are infinitely many graphs, right? And they reduced it down to a finite number, but it was like insanely big, much bigger than any human could possibly check in a lifetime. But a computer can check things faster than a human, so they asked the computer to check it. And this is like philosophically a bit of a weird situation, because it's sort of impossible for mathematicians to independently by hand verify the proof. They need to ask a computer, is it true? And at the time that was a bit of a weird thing to do. Okay, so that's the four-color theorem, and that's the end of this video.